Okay, thanks very much, Urja, and thank you very much, all of you, for attending. So, uh, as stated, the title of my talk is the Einstein-de Haas effect. I'll periodically stop. I have, I think, presentations maybe about half an hour, so there's lots of time for questions, and I'll stop periodically and ask you if you have any questions or comments. So, uh, sort of start with a. This is more like a history of physics type talk rather than something that's at the leading edge. Everything I'll be discussing are things that are known, uh, but I feel this type of looking back and understanding how our current knowledge came to be is something that's very valuable. So there's this famous quote from Niels Bohr, quote unquote, physics is the history of physics. And I like this photograph because it's very hard to find a photograph of a physicist on a motorcycle. Anyway, yeah, well, I recently also heard somebody say that it's a sort of a slighted insult to say somebody is interested in the history of physics, as if they're not interested in the leading edge of physics. That's the sort of implication. They're interested in the history of physics. But I'll just mention this that in the last year, Steven Weinberg passed away. He won the Nobel Prize for the discovery of uh, the how to unify the electroweak and electromagnetic forces. And he won the Nobel Prize for that. And so that's a kind of critical part of the Standard Model. And he was a prominent physicist who was extremely interested in the history of physics. I mean, it's really unfortunate. He wrote some very nice books. He wrote a quantum mechanics textbook, which is very good. And he also wrote several, well, at least one history book. And every one of his books has a kind of nice history aspect to it. But about 5 years ago or so, maybe a little bit longer, he wrote a book called To Explain the World, which I'd highly recommend to anyone because it's sort of unique in the sense that it's a history of physics book, but it's by somebody who contributed to the leading edge of physics. And that's a sort of unique perspective. Of course, he got severely criticized by professional historians for his viewpoint. But I think that the whole book and the controversy behind the book is very interesting. So anyway, some physicists like the history of physics and some don't. Niels Bohr apparently did, and so did Steven Weinberg. So, what is the Einstein-de Haas effect? Well, it relates to magnetism. Now, it used to be that there were these two sort of separate phenomena. You had voltaic piles, so you generate currents and electric shocks and so on, and then these things, you could find these rocks and eventually you could make materials that attracted one another, the magnetism effect. Now, there were already sort of a hint that these two phenomena were related in the sense that lightning strikes tend to magnetize materials, so a large amount of current flowing. But nonetheless, they were sort of viewed generally as sort of disparate phenomena. Now, Oersted, he was preparing for a lecture one day, and he found, almost by random, that when he ran a current through a wire and he had a magnet nearby, then that magnet tended to deflect based on the current in the wire. And so that was the sort of start of seeing that these two phenomena, electricity, okay, the flow of this current, and magnetism, a bar magnet and how it would be oriented, were connected. Now, so if you think, okay, so in the history of this subject, what's the next kind of natural experiment? And that was that if you have two wires and they're both carrying currents in the same direction, then they'll tend to attract, okay? And if they're carrying currents in the opposite direction, they'll tend to repel. And that's something that Ampere discovered. But he also made a hypothesis based on this observation, and he said, okay, If this is what happens when you have two current carrying wires, and we see here that there's a connection between magnetism and a current carrying wire, then maybe we can understand all permanent magnets somehow of being uh, the reason they're magnetic is because inside of them there are circulating currents. So this is known as Ampere's hypothesis, and I've sort of put belief here because he really didn't have any strong evidence that this was true. It just seemed like something that would be logical. So what's the picture here? Well, here I've sort of drawn a loop of circulating current, and I've drawn a bar magnet with a north and a south pole. So what do you know about magnets? You know that if I have a north pole and a south pole, and I have another magnet, a north pole and a south pole, well, these two ends attract, right? And I'll get the opposite situation. I'll get repulsion if I flip them around so that either the north poles are meeting or the south poles are meeting. So how would I explain that from a current point of view? Okay, so if there are molecular currents, well, imagine I have a current like this, and I have a current like this, okay? They're both in the same sense. Sorry, I'm not a very good artist. Well, then, because they're parallel, these two currents, when they're close to one another, I should have drawn them really close, right? Then, and they're in the same direction, they would attract in the same way that the two wires attract here. Whereas if I reversed the direction of the two loops, if I had one loop like that and the other loop going in the other direction, they would repel. So you see that this picture of currents repelling and attracting sort of explains, or you could imagine the way magnets work based on these loops of current. Okay, any questions or comments at this point? Okay, so what's the sort of simplest? This is something you learn. I'm not sure of the distribution of years of students here. So I'll some of you have seen this already in Phys 342, let's say, the third year lectures in magnetism course. But this is the sort of simple way that you model the magnetic field based on our current understanding, the way that you model magnetic field due to a circulating or a circular loop of current here. So the field lines are these green lines, and this is the circulating current. And so the main thing here is that you characterize the only thing when you're far away, let's say out here, when you're far away from this loop of current, the only thing that matters is basically the current I times the area of the loop. And that quantity pointing in this direction is known as the magnetic dipole moment. Okay, so you imagine that, okay, if the material is made of these little circulating currents, well, they're probably little small loops, right? Based on the idea that atoms are small. If this is what, Ampere's time and before our modern knowledge, right, of magnetism. So so if you care about what the magnetic field is due to this little loop, you care about what it's far away. And as far as when it's far away, all you care about basically is the magnitude of the current in that loop and the area. Okay. So for example, if you take that magnetic moment, which we'll call mu, and you put it in a magnetic field, the torque on the dipole is mu cross B. So for example, if I have a magnetic field that's pointing upwards like this, and I have a dipole like this, it'll tend to either orient away from or towards the magnetic field, okay, based on this torque expression. So that's the idea that if you have a magnet, it will want to align in a field in the same way that Ørsted discovered. As I say, he discovered this when he was preparing for his lecture. Unfortunately, I haven't made any discoveries yet when preparing for my lectures, but I live in hope. Okay, so what's the picture here? So you would say, okay, so our north and south pole picture, you would think of a material being these sort of made up of little magnets that have north and south poles, okay? But when understood in terms of Ampere's hypothesis, that's equivalent to a bunch of little dipoles here, circulating currents, and something that we call the magnetization, M here, is the number of these dipole moments per unit volume times the magnetic dipole moment of each, okay? Where the magnetic dipole moment was what we've just discussed here, okay? The current that's circulating around here times the area of the loop. Okay, so the interesting thing here is that if you have a little circulating current, and it's due to, and that's mass that's circulating, okay, not just charge, right? But that charge has a mass, then when you have a circulating loop of current, you also have an angular momentum, okay? So there's a very simple relationship. Again, you go through this in third year, so this will be very familiar to some of you. And that important relationship is the relationship between a magnetic moment or magnetic moment and angular momentum. Okay, so all of you have done angular momentum in first year, so that'll be familiar. And again, to some, the magnetic moment is new, but this is all straightforward. So we start with this definition of magnetic dipole moment here, and we just write it in a slightly different form. So we say, okay, well, to get this current, okay, I need to know how fast this electron is going around the loop, okay, and see how many times does this, if I sit at a particular point on the loop, how many times per second does this charge go by, and what is its value? Well, that's I. So I basically take, okay, so I replace here pi r squared, and I take q over the period, and the period is 2 pi r divided by the speed that this electron is traveling around, and I get this this expression finally in terms of the radius of the orbit of the electron and the speed. Now, okay, this is, you may be repulsing right now and saying, oh, hasn't this guy ever heard about quantum mechanics? Well, I have. And it turns out that this very simple picture that I'm describing also works in quantum mechanics, okay? Now, so we have this relationship between magnetic moment and our crude classical description of an orbit of an electron in terms of the radius of the orbit and the velocity and the charge. Now, what about the angular momentum? Remember, we're looking for a relationship between this quantity, the magnetic moment, and the angular momentum. Well, that's r cross p, okay? So what do I have? I have v times r, so actually I should have a mass here, right? Not q. Okay, that seems to be actually a mistake, right? Okay. rv in terms of the angular momentum of the yes, okay. So if I go back and I say, okay, well, now what's the relationship? I don't think there should be. The other thing that I'm noticing here is there shouldn't be a 2, right? There seems to be a lot of mistakes here. Okay, so if I say, okay, now what's the relationship between the magnetic moment and the angular momentum? Well, I have RV, a factor of RV here, and a factor of RV here, and then I have a Q over 2 and an M. So if I take the ratio of these, they point in the same direction, Z hat here. So if I look at the ratio of their magnitudes, I get Q over 2m, okay, from this Q over 2 factor here and this M factor here. So now, okay, so what should I use? So you'll have to believe me, if you did the same thing, you'd get the same thing in quantum mechanics, okay? Now, what should I use for Q over M? Well, okay, so back in Ampere's day, they wouldn't know, right? If there was something circulating around in a loop, they wouldn't know what should I use for the charge and what should I use for the mass, okay? But eventually, we discovered the electron, right? So if magnetism is due to electrons moving around in circles, then we in principle know the relationship between the magnetic moments of a material and its angular momentum. Okay, so now, okay, you could say that point-like particle that we're imagining circulating around, maybe it has some structure. Like maybe there's something big that's rotating, and all the charge is in the center. Okay, that's one extreme. In which case, you can have a lot of angular momentum and no magnetic moment if all the charge is concentrated in a point in the center. Or you could have something where all the mass is in the center or concentrated in the center, and then the charge is on the surface of the material. So it's become traditional. But if the structure stays the same, that charge and that charge distribution and the mass distribution, as you spin the material more and more, you'll keep the ratio of the magnetic moment and the angular momentum to be the same. So because of that, that the charge might not be in exactly the same place as the mass, okay, that the mass density and charge density aren't necessarily proportional to one another with the same factor all throughout the material, we introduced this factor called G, okay, that's a correction to whatever this ratio of this magnetic moment should be for a point charge, uh, uh, for just a compared to just a circulating point charge. Okay, so this is dimensionless. Okay, so let me stop and ask, are there any questions so far? Yeah, yeah, please feel free to ask. Okay, okay. If someone uses the chat, because I don't have my computer set up, would you mind calling those questions to my attention, Urja, please? Okay, great, great. Thanks very much. Yeah. Okay, so now we get to Einstein's time, uh, and okay, by this point, people knew there was an electron. J.J. Thomson had measured its charge to mass. We kind of had this idea that that electrons are the things that move when currents take place. It's not the nuclei that move; it's the electrons that flow. So then the question was, well, can we verify and see, is magnetism really due to little circulating loops of current in a material? Is that the cause of why materials are magnetic? So in terms of the language that I've used here, where I've introduced this G, okay, if you found that G was not equal to 1, okay, where you if and you used the charge to mass of an electron, if you somehow could measure angular momentum and measure magnetic moment and thus deduce what what this overall factor is, and then stick in the charge to mass of the electron, which was known, then you could see, oh, is G 1? Is it like these circulating point-like things that are electrons that are causing the magnetism? Now, if you get 1, it's one of these tests, right? If you do get G equals 1, then do you really know that it is electrons? You could have sort of competing effects that cancel out or balance out. And so it's more like a sort of test that if you get G not equals 1, then you'll say, oh yeah, okay, it's definitely not the electrons, right? Or if it's the electrons aren't point particles. They have some weird mass charge density distribution. If you get 1, well, it's always the same thing. You can never really conclude anything from experimental physics. You can just kind of rule stuff out. Okay, so G equals 1 is not so clear. Okay, so in 1915, this was a very interesting experiment. So you sort of remember the timeline of Einstein, okay, or maybe you don't, right? But 1905 was special relativity, the patent office, right? And between there and 1916, he became a sort of well-known figure in the physics community. He went from being a patent clerk to being a professor and working on general relativity, which was kind of ironed out roughly around 1916. So Okay, so we'll get back to Einstein and what his role and De Haas's role was in was in a few slides here. Okay, so here's the idea that their experiment was based on. Let's say, okay, not all materials are magnetic. Most materials aren't magnetic. A piece of wood isn't magnetic. In fact, even materials that can be magnetic are not necessarily magnetic. If you take a piece of iron, right, you maybe be familiar with the idea that you can magnetize it. Some materials, like permanent magnets, well, they're sort of magnetic all the time, and maybe you can make them worse magnets by heating them up and so on. Then there's materials like iron where you can magnetize it or you can demagnetize it. Okay, it's permanent magnetism is a variable, if you like, right? So in Ampere's picture or idea, this is what a piece of iron would look like when it's unmagnetized. You have all these like circulating dipoles, but uh, there's no sort of net effect. The average direction of the dipole moments that they point is a random direction. So what happens, let's say you stick this thing, let's say you bring another magnet, or you bring a material that is magnetized nearby, or you put this thing in a solenoid that generates a magnetic field by a current, okay, then you'll get all the dipoles to be aligned, okay, and then the material is magnetized and it has a non-zero magnetization per unit volume. Now, I kind of like anticipated, unfortunately, I'm sure like the rest of you, that we would be doing this in person. But let me give you a virtual demo here. I'm sure you've all seen, you remember in first year, this demo, maybe Richard Epp did it or so on, whoever your first year physics professor was, where you take a bicycle wheel and somebody turns the bicycle wheel around and around like this, and then you rotate. You have a person and they're sitting on a turntable or like a swivel chair, like this chair that I'm on here, and they take the spinning bicycle wheel and they bring it up so that it's rotating around like this now. And what happens? Well, the person starts to rotate in the opposite direction from the spinning wheel, right? And that's a very, very basic demonstration of the conservation of angular momentum, right? You had sort of net angular momentum around this axis when the wheel was like this, okay? It's a completely internal system where there are no external torques being applied. So when you raise the wheel to get a conservation of momentum, you have to have two angular momenta about this axis that cancel. Okay, so that's a great demonstration, right? That you've probably seen before. So you kind of expect that that must happen here, right? These are all these little bicycle wheels that are turning around, having angular momentum. And when you make them, when you orient them, whoa, is there conservation of angular momentum here? There should be, okay? Now, remember I discussed earlier that they'll be magnetized by sort of, where did I discuss this? I think we discussed this back here about a torque. So there is a torque that's applied to these dipoles to orient them, but the torque is in the XY plane, not in the Z plane, okay? So it doesn't explain. I mean, the torque is like this, right, that you're turning. It doesn't explain or can't explain or can't get rid of the idea that it appears that momentum isn't conserved around this axis, okay, corresponding to this type of spinning. So what's the resolution of this apparent lack of conservation of momentum when you magnetize a material? Okay, well, in principle, when you do this, the material itself, the bulk material, will try and spin in the opposite direction in the same way that with the bicycle wheel example, when you rotate that bicycle wheel, you spin in the opposite direction to conserve momentum. So you can set up an experiment to try and see this effect, right? So I mean, basically the idea is that L total, okay, or at least its projection along this z hat axis is 0. And when you magnetize the material, okay, if ampere is correct, then you have these circulating currents and you have an angular momentum associated with those circular currents, then the cylinder must start to spin in the opposite direction. And this is known as the Einstein-de Haas effect. And I'm not really sure, I mean, who uh, I'm not really sure who first kind of proposed this should happen. In a certain sense, it's sort of basic first year physics if you accept Ampere's hypothesis, right? But they're certainly the first people to try and measure it or try and get something quantitative out from it. So what they had is, maybe you remember in first year, sometimes you make torsion pendula. Okay, so you have, like, in this case, it was sort of a thin piece of quartz wire, and you might, like in first year, you might have used a very thin sort of rod where you have a mass at the end of that rod, and if you twist the mass, then it will start to rotate, sort of twisting, undergo an oscillation of twisting back and forth, right? Okay, so they put a magnet, a piece of iron, okay, something that was not necessarily magnetized here, but could be magnetized with an external field. They put that on the end of a fiber, and then they also put two coils that they could make a magnetic field by circulating macroscopic currents. Okay, these aren't Amperian currents; these are actual real currents that, all the way from Ørsted's time, we knew that they were connected with magnets. Okay, so and then the idea was basically you would magnetize this piece of iron in here, and you would look to see how much did it twist. Okay, when you magnetized it. Okay, so what kind of kick in angular momentum did it get? Okay, due to this idea that once all the dipoles line up, you have to have a compensating angular momentum in the bulk of the material. And the way they made the measurement was they shone light. This is kind of like, would be a kind of classic laser experiment now, but they shone light off mirrors, and then they observed it far away. That's how they made this measurement. And this sort of gap here is for their observations of the light. Okay, this mirror is in this gap between the two coils. So you might wonder, something that's very interesting is that this experiment was done, I forget exactly the year, I think it was 1915. I've got a date later on the slide, and that's weird because that's all around the time that Einstein was working on general relativity. So you might say, oh, okay, well, maybe De Haas was the guy turning the wrenches in the lab, okay, making this thing happen, and Einstein was doing all the calculations. But that's, in fact, that may be true to some extent, but it's also clear that Einstein actually did work on the experiment. I forget where in the Netherlands, if De Haas was in Amsterdam or Leiden, the two kind of centers for experimental physics in the Netherlands at the time. But Einstein actually did work on the experiment. You can see this quote to his friend Besso, where he's saying the older he gets, the more sort of he likes experiment. It's a kind of somewhat humorous quote. So what were they? What did you want to get quantitatively out of this experiment? You wanted to see what that G was, okay? That sort of correction to the ratio of the magnetic moment to the angular momentum. Okay, so I'll discuss that in a second. We're getting pretty close to the end here. So, but I'll just stop to ask, are there any questions so far? Okay, great. Okay, yeah, so that's okay. So when do you learn about oh, okay, so let me answer the second question first. Okay, so some of you, I guess, will be in second year and first year, and you're wondering, when do you learn about like what magnets are, right? Sort of like one of the kind of it's like a sort of meme, right, of like physics, right? Like what is magnetism, right? And yeah, it's actually it's why I went to university to study physics. Is I was interested in what magnetism was, right? And I looked through the course descriptions for the different programs, and I saw that engineering took every topic in that like we took in like 2 years or 3 years in physics. They did it all in first year, and I thought, how's it going to be possible to understand all of those in like 1 year in a one-term course, right? That can't be possible, right? So anyway, I think that's true. So you really get into the details of learning about magnetic materials in Phys 342. Okay, so I've taught that in the past. Don't think I'm teaching it in the future. But okay, so that's the course situation. That's the third year lectures in magnetism course. But what's the difference between magnetizing and demagnetizing a material, or a material that can be magnetized and cannot be magnetized? It's just the difference between these two pictures. So this is demagnetized. All the all the dipoles are pointing in random directions. So if I brought another cylinder here beside this one, and let's say it was magnetized, so this is magnetized, okay, and I have all the dipoles and they're all oriented in a specific direction, unlike this one where they're all in random directions. Well, some of these dipoles will repel, and some will uh, attract, right? So uh, there'll be no net force here between them, right? But if I take, for example, this material and I say, okay, I have at the end, I have a dipole like that and I have a dipole like this. Well, since two currents, since these are near one another and currents that travel in the same direction attract, then this, this material up here, this is its south pole, and this material down here, this is its north pole, will now attract. So that's sort of the difference between being magnetized and demagnetized. Now, so how do you magnetize a material? Well, you take a material like this, where all the dipoles are point in random directions. Not kind of a very good artist, as you can tell here. And you run a big current, okay, through big loops of wire, okay, so a current that you generate with a battery or a voltage source, and that makes a magnetic field in this region, okay, and that magnetic field tilts or turns these dipoles so that they align with the magnetic field, okay, so it's kind of like part of the dipole gets pulled up and part gets pulled down, so that the dipole orients with the magnetic field. Okay, so that's really, this is just another version of if I take a bar magnet with a north and a south pole and have another bar magnet up here, well, the south pole will go like this towards the north pole, and if it's in this direction, it'll try and flip over very, very quickly, right? So that's magnetized and demagnetized. Is that yeah? If I sort of answered the question there. Yeah, there's a classic. That reminds me, a kind of classic demonstration. Uh, so these materials, sometimes materials. Okay, so when you magnetize a material, that's I'm not explaining the full picture. When you magnetize a material and then you take away the magnetic field, it can some materials will stay magnetized, and some materials, when you take away the external magnetic field that you're forcing them to magnetize, well, they'll just demagnetize again. And for some materials, whether or not that happens or not depends on the temperature. And so maybe you've seen the idea of, like, if you have there's some neat demos on YouTube and so on. You take the poles of two magnets and you put like liquid oxygen in there between the two poles, and it'll sort of stick in between the two poles. And that's liquid oxygen, and oxygen in general is an example of a type of material where you apply external magnetic field, you orient all the dipoles, but as soon as you take away, like you mentioned, liquid oxygen probably isn't a permanent magnet, and you would be right, right? As soon as you take away the external field, well, all the dipoles kind of randomize their directions again. So let's get to the exciting part here now of their experiment. So uh, somebody said, sorry if you've heard this before, I'm sure upper year students have heard it before, is that the whole career of a theoretical physicist consists of just solving the harmonic oscillator again and again with increasing amounts of sophistication, right? So if you're in first year and you don't like simple harmonic motion, I've got bad news for you. So, okay, yeah, sure. I don't know of I don't know of. I'm hesitant. Yeah. So the question is, can fluids be permanent magnets? And uh, offhand, I don't know. Uh, I think there are suspensions like where you can have sort of a colloid, and it can be. I don't know if it can be permanently magnetized. I mean, sort of oxygen. Oxygen's the kind of classic example of a liquid that's paramagnetic, so you can induce a magnetism and then the magnetism goes away, so it's clearly not a permanent magnet. uh, I'm having trouble uh, thinking of uh, something, a liquid that would be a permanent magnet, but I don't know. I'm hesitant to say that that can't happen or doesn't happen, just because yeah. uh, I don't know. Yeah, yeah. It's a very good question. Yeah, 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 yeah. Yeah. Well, I'll try and find the answer for that. Yeah. Okay. So what happens uh, when we look at the quantitative detail of this torsion pendulum, this sort of device here that we're discussing? Well, the fiber, like the pendula that you would have studied, torsion pendula, where the motion is twisting, there's a sort of restoring torque depending on how much you twist the angle. So that would be this, okay? And no surprise that we use K here, sort of like the spring constant, even though it's a sort of slightly different type of elasticity. And oh, there'll be a term that looks like m times the acceleration, only we're talking about angular motion here. So it's the second derivative of the angle times the moment of inertia of the device. Okay, so that's all known. What is this? Well, that's the damping, right? So if you started this thing oscillating, eventually the the oscillations would die out. So that's this term here. And then this thing, let's say we magnetize it, we apply a current and we magnetize uh, the iron rod, and then we turn around the magnetization, make it go in the other direction. Okay, we keep on reversing the direction. That's sort of like a forcing term. That'd be like the person kind of pushing a person on a swing, right? So that's this term. Okay, so we have a name for this. I mean, it's in a slightly different context than you would usually see it, but it's a driven damped harmonic oscillator, and its frequency depends on the spring constant, quote unquote, the spring constant, only for angular motion, and the moment of inertia of the device. So the basic idea here is if you repeatedly magnetize this material back and forth, you're kind of twisting this pendulum, and if you see, okay, how much am I magnetizing the material, which you can measure with some external device, see, okay, this is how much I've magnetized the iron in one part of the cycle, and then I've magnetized it in the other direction and so on. That's the force that's driving this pendulum. If you can measure the magnetization and you can measure then the amount of motion, okay, so essentially the amplitude of this angular motion, then hopefully you can back out G, okay, this ratio or this correction to the ratio between the magnetic moment of the material and its angular momentum. So now there's a little bit of a problem here, uh, and I don't have this written up as well as I should, but the magnetization you can measure, the angle you can measure, that was the purpose in that light beam in Einstein-de Haas's experiment. This term, the damping, that's actually kind of hard to measure. Now, so how do you measure it? Well, what you do is this is taken from a first year physics textbook. This is a kind of bad example because I should have credited where I got this plot from. But basically, this is the idea that, let's say, so what do you have here? You have the frequency that I'm magnetizing that iron material back and forth. And what's plotted here is the amount of angular oscillation. Okay, so the amplitudes of the oscillation that this piece of iron is undergoing. And what you do is there's a natural resonance frequency here, which depends on, as we said, this spring constant and the moment of inertia. So that's where if you drive this thing resonantly, you get the most motion here, okay, the largest angular displacements. But if you measure the width of this resonance, okay, so by varying the driving frequency at which you're magnetizing that iron and measuring how off from the resonance the amplitude decays, then you can figure out from the mathematics of the driven damped harmonic oscillator how what that damping factor is, what this quantity is here. And you need that gamma to back out and figure out what G is from the measurements. So, okay, what's the point here? Maybe should have gone into a little bit more detail about how this works, but the point is a very, very simple, well, maybe it's a mistake to call it very simple, some simple ideas about harmonic oscillators and damping and resonance were all very critical to this experiment at the leading edge of physics. Granted, the leading edge in 1916, but nonetheless, those ideas about damped harmonic motion and so on that you're taught in first year are actually useful. So, so this is some of their measurements of the resonance, and so from this measurement of the amount that the iron rod was twisting back and forth based on the magnetization, and assuming that the currents were due to the electron, they got G equals 1, okay, to within their estimated experimental uncertainty. Okay, so again, back here, I said that was a pretty strong test of Ampere's hypothesis. Okay, so is magnetism really due to these electrons going around in circles? So, and we kind of said, well, if you got G not equal 1, well, then you could rule out Ampere's hypothesis. If you got G equals 1, well, that's sort of like good evidence that Ampere's hypothesis is true, but it's certainly not a proof because you could have canceling effects. So that seemed like hey, we did what we did the experiment, and we kind of proved that Ampere was correct, right? That's a sort of simple story, isn't it? Well, not quite, and that's the sort of point here. Is so here's Einstein-de Haas's measurement, 1915. Okay, so this is the year. So this is 1915. This is whatever 1921. Okay, etc. And then it was a sort of modern quote unquote modern measurement here in 1962. And this is G. Okay, so remember, Ampere's hypothesis is G equals 1. Okay, so Einstein-de Haas, okay, 1 plus or minus 0.1, 1915, first experiment. Now, there's a sort of complementary experiment. I won't explain the details of it, but it's a sort of like a duel, if you like, where you take a piece of iron and you start to spin it, okay, and you look to see does the material magnetize when you start to spin it. And that type of experiment you can also try and figure out what G is, again using ideas from conservation of angular momentum. And a fellow named Barnett, he worked at the Carnegie Institute, he got these numbers which are very different, almost twice. So this is 2.2 here. He got almost twice the value of Einstein and de Haas around the same time. Now, okay, already by 1915, Einstein was a well-known person, right? Special relativity was, basically was generally accepted in the physics community, special relativity and photoelectric effect and Brownian motion. He was a quite respected person at this point. So one interesting thing that happened was Barnett then redid the experiment. I don't know why there are no error bars here. And he got something which was close to Einstein and de Haas, but not exactly the same. Now, you see sort of what happened as history went on, and this guy Scott, there are very small error bars on this value. You see that actually G is approximately 2, according to these modern measurements. So what went wrong? Okay, we went from 1 to now our sort of current understanding of 2, and Barnett actually basically got 2 initially, right, with this complementary experiment. So the idea is that the exact mechanism for magnetism is a bit different in every material, okay, but it consists of 2 parts. One is definitely potentially the orbital motion of electrons. That for sure can contribute to magnetism. But in iron, okay, that was the material they're using, the electron itself has an intrinsic magnetic moment. It behaves like a little bar magnet, okay? So it doesn't have to be moving around in a circle to generate a magnetic field. It has an intrinsic magnetic moment. Now, and that's associated with its spin, okay? So there is a very well-defined relationship between the spin angular momentum of an electron and its magnetic moment, okay? But the ratio between the magnetic moment and the spin angular momentum is not Q over 2m, which you'd expect from a classical kind of theory. It's twice that. It's Q over m. Okay, so that's G equals 2, and that was essentially the first explanation for that was by Dirac in the 1920s. And so when you get to 4th year, you'll study Dirac's equation, which is the first sort of, it's the relativistic version of Schrodinger's equation. Okay, now in fact it's for an electron, it's not exactly to a bare electron. There's a little bit of a correction, okay, due to the fine structure and the fact there are oscillating quantum fields, electromagnetic fields, that change that from G equals 2 to something that's a little bit different. And that's the whole story of the thing that Feynman was involved in, the explanation of quantum electrodynamics. Okay, so in iron, the magnetism is basically due to orienting electrons, and it's not due to electrons themselves executing circular loops of current, but just that intrinsic spin angular momentum. So when you do this measurement very well, like was done in the 60s, you get something which is very, very close to 2. So the question is, what happened? I mean, they were using iron here. Well, we have no way of knowing. I mean, historians have looked at this and tried to figure out. I mean, nobody seriously suggests that like they said, okay, let's just reproduce what Ampere, let's just try and fudge our numbers so that we get what Ampere predicts, right? I mean, they in these at this time they had no idea of the intrinsic angular momentum of the electron. Okay, so there are various ways that you could kind of ideas that you could criticize their experiment and say, okay, well, how could they get the wrong number? Okay, but you have to explain a little bit more than that. It's not just the wrong number. Uh, it's the wrong number that agreed with what people thought was the theory of the time. So there's always this bias that you have when you do experiment. Everybody has it, including me, right? You try and get rid of it, right? And it's basically the following: you know what you think you know what the answer should be. You make a measurement, and your measurement is slightly off, right? Well, okay, then it's natural to start looking for things which would explain that discrepancy. But that in itself is normally a kind of subtle bias because in general, you only try to look for effects which bring you closer, okay, to what you expect. You'll rarely say, okay, these two numbers disagree. What would make them disagree by even more? It's a natural human thing to not do that, right? And so when you try and search for systematic errors in your experiment, not random errors, which you can treat with the properties of statistics and repeated measurements, but when you look for the systematic errors, you have to be very careful to guard against a bias which only uncovers systematic errors, which push you closer to what you expect. So so people know about this, right? And this is a very well-known phenomenon, right? So that's why in the gravity wave detection experiments, they had these test signals that they would try and inject into the system, okay, and see, okay, is everything working? How are those things detected, and so on? Like they'd introduce fake signals, but only some people actually knew they were fake signals, and so it's sort of like very common thing to do in very high precision metrology is to hide from everyone the value of a key calibration of one of the instruments involved in the experiment. Let's say you're making some microwave transition. Well, you put like a little, you have to run the synthesizer and you leave sort of an unknown part that people don't know. It's written down somewhere, okay, somebody has this information. So you go through your experiment, you try and analyze it, you look for all the systematics, right? And then you say, okay, this is my best number, except I don't know this one number because it's a hidden key. And then finally at the end, you bring in that hidden key when everything is done and you say, okay, that's my result, right? So what you've done is you've kind of tried to find all the systematics, okay? But you've done so in a way that hopefully hasn't biased you towards your previous expectations. So that's a very well-known thing in modern precision experiments. And I think Einstein-de Haas's experiment is very illustrative because it shows that what we can't prove this. It shows what happens when you expect a result. In general, sometimes you can get it if you try hard enough. So. I mean, I don't think there are some people who have sort of different ideas and thinkings on this subject. They kind of say, "Oh well, how could how could you even dream of criticizing this great man, right, Einstein?" Well, to me, it's not like that at all, right? It's just very, very interesting. First of all, it's extremely impressive that he was interested in experiments and did this experiment. And I don't know, there's some sort of element I feel of like knowing what a person's mistakes were or what people were mistaken about in the past. Kind of, yeah, it's interesting. It informs your thinking and your view of things. There's a whole book by this guy Hans Ohanian. I find this, I personally like this book. It's pretty interesting. He sort of goes through all the mistakes that Einstein made in his career, including, there's a famous one where he said, well, gravitational waves don't exist, right, or can't exist, and so on. But there's a little bit of I don't know, there's a little bit of sort of element of this German word, right, which I won't try to pronounce, but means taking pleasure in someone's sort of downfall or mistakes, right? But for this history of G measurements, there's a very nice book by Gallison, How Experiments End, that I sort of recommend if you're interested in looking into more of the details. And as far as Einstein goes and his participation in this experiment and his whole life, this is a wonderful biography. Subtle is the Lord, and it talks about this experiment. It talks about the problems, but mostly it focuses, on his great accomplishments. So anyway, I thought this is a nice picture here to end with, where you have Zeeman of the Zeeman effect and Einstein and Ehrenfest in a laboratory. So as far as I know, this is the only photograph of Einstein in a physics laboratory. So I thought it was sort of nice to put at the end here. Okay, so thank you very much for your attention, and I'm happy, if you have any questions and so on after the presentation, just send me an email. I'm easy to find, I'm sure, on the department website, but I'm jddmartin at uwaterloo.ca.